Okay, now we come to two slides, and these are two slides, and I'm sure you guys over the years with your experience with MapReduce have seen enough of similar slides to these, if not the same. Okay, now I have put these slides not for the purpose of repeating what mappers, combiners, and partitioners and shuffle and sort are, or for that matter things on this next slide as well. The very purpose of putting this slide is only to make you thinking in terms of the tools which MapReduce provide, and these are actually the building blocks around which most of the design patterns are built. So I'm not going to belabor you with details about these two slides. Just put it for the purpose so that you have in front of you a picture of how this whole framework works. And this is important because, for example, if you look at the blocks here, which is meant for the sort. Okay, now the important thing about it is you can provide your own comparators to these sorts. So you can provide your raw comparators as far as the sorting which happens on the mapper side is concerned, and on the reduce side, the group sorter. So the thing is, you can provide your own comparators to that, and the effect of that turns into you having an algorithm which helps you do secondary sorting. It's very important for you to understand each of these blocks properly and how you can use these in different ways. So let's. So now you start with why you actually require design patterns. We want to broach this topic with a sorting example. I'm not going to give you a code for the sorting example here, but just for the purpose of starting a discussion around why you require MapReduce design patterns. So if you have, for example, you're sorting on a single machine, you're doing a million record sort, then of course quick sort and merge sort are the algorithms you will definitely go ahead and use immediately. But now the problem is, if you have a data which is 1 trillion, of course you cannot sort that on a single machine. You'll require a parallel computing framework like MapReduce. But the question is, can you directly use quick sort over here on this framework? The answer is no, because the very structure of this MapReduce framework would not allow you to do that. Saying that I won't allow you to do that is wrong, but for example, see, any of these quick sort, merge sort algorithms will require an iterative processing of the data set. Okay, now if you look at MapReduce as a framework, you start with the mapper, you reach the reducer, and that's it. Okay, so one iteration you do, your job is complete. You have to look for innovative ways of using what this framework provides to be able to implement different standard algorithms on this framework. Also, from the perspective of the limitations which the framework forces on you, so that you cannot go ahead and use the mappers or the reducer in the way that you want to. For example, any synchronization that has to happen across the processing which has been done by these mappers and the reducer stage, there is only one stage where you can do that. That is the shuffle and sort. Apart from that, in most of the other stages, all these jobs are all these mappers, reducers, or any other process is running completely independent of each other. So that forces independence in the sense that you don't have much of a control. Okay, that kind of tells us that standard algorithms as they are, they do not exactly fit into the framework if you just bring it on like that. For example, just okay, so let me spend maybe a minute to think about it. So if you have to implement quick sort on Hadoop, so the way quick sort works is you divide your data and then you start merging your data together. Okay, in between you do certain operations on the data. So there's a very specific kind of a control which is imposed here as far as algorithm is concerned. If you try to do that on MapReduce, you will miss those controls, and actually you will end up you will have to do a lot of jobs which would have to be chained together, and even then it's going to be very difficult to implement that. Let's see some of the constraints and the techniques which the framework provides us. And I'm sure you guys already know a few things about it, or maybe everything about it. So map tasks include rigidly defined stages that must work together in specific ways. But it's possible to recast your algorithms in this framework and solve problems at scale. And actually, as part of this course, we are going to be implementing some of the graph algorithms, and one of the algorithms that we'll implement is a page rank algorithm, and we'll see how we can implement such complex algorithms on MapReduce. Although, if you look at any of the graph algorithms, they do not fit exactly into the structure of this framework, but we can still use this framework if you understand some of the patterns. Okay, so these are the constraints. Programmer has very little control over many aspects of the job execution. Where a mapper or the reducer runs, when a mapper or the reducer begins or finishes, which input key value pairs are processed by a specific mapper, which intermediate key value pairs are processed by a specific mapper. You ideally would have liked to have such control in your hand, but that control is not provided to you. So those are the constraints, but it does have a lot of techniques and tools for you, and that's where these frameworks excel. And these tools help you do things in such ways that you very complex kinds of algorithms actually can be fit into these patterns. For example, ability to construct complex data structure as key and values. You will see these things being used as part of the filtering pattern and the summarization patterns. Then you have user-specific initialization and termination code at the start and the end of MapReduce jobs. These are the start and the close things which run before each of your map jobs run. Ability to control sort order of intermediate keys. This is done through the sorting part that I talked about earlier. This is done by using some of your own comparators implemented. Ability to control the partitioning of the key space, you know this pretty well. So this is the hashing which is done by the partitioner, or by default you can go ahead and change that behavior. So yes, so there are some of the reasons why you should definitely learn about these patterns, because you could be writing different kinds of code, and for example, some of the people who are involved in writing application code and doing analytics maybe on a log file, and if that computation is not too complex, then some of these design patterns that we'll talk about, a lot of these things would fit in without much changes. They'll fit in without, of course you will have to make changes based on the domain in which you're working for, but as far as the pattern itself goes, they would be quite apparent if you are designing such code. But there are cases where okay, so yeah, so so that's not all. So there are very complex systems are made on top of these MapReduce things. So for example, think of nudge. Okay, so initially that cutting had been writing nudge not on MapReduce, but he actually faced a lot of problems doing that. So he later on he shifted these things onto MapReduce. and today it actually runs in MapReduce. Think of a system like Mahout. Okay, so Mahout again runs on MapReduce, but if you look at the crux of that algorithm is mostly about doing machine learning. All right, so some of these very complex things have been adopted on MapReduce. Now, if you want to write a system like that, such complex systems, so there is a domain knowledge involved over there, and then there is knowledge of being able to adapt that stuff onto this framework. Okay, and definitely if you understand MapReduce design patterns, it makes your job a little easier than you would be without knowing these patterns. If you have any questions, you can keep on sending them out at different points in the webinar. Probably I'll just have a look, and maybe at the end of it, I will try to answer some of those. Okay, so I'm moving on to the next one here. Yes, so now we have seen why of the MapReduce. Let's see what are these MapReduce design patterns. Okay, what types of patterns actually exist. And as I said earlier, this is actually an evolving list and will keep on evolving as inputs come in from the users of MapReduce or the tools which have been built. For example, Pig. Pig itself is one of the tools which drives patterns into MapReduce. And then, of course, some other systems, for example, I'm not sure if Nudge has driven any patterns into it, but systems like those also, based on the requirements, can drive some of the evolution in this field. Okay, so one thing I would like to specify, there is a book on MapReduce design patterns, and a lot of this course I have based on that, and these patterns are actually from that book, and that's in the reference. So summarizing patterns are basically patterns which give you a very high level view of the data. So you want to do high level analytics on something before you want to go deeper into understanding the data. So quickly you will do some of these summarization patterns and understand your data. What happens is your actual data doesn't change, but the view of the data that you get is a summarized view of the data. Some of the patterns which come into this, actually the filtering pattern, which I'll, sorry, not the filtering pattern, the inverted index pattern which I'll talk about, is a kind of a summarization pattern. When we look at the filtering patterns, these are, as the name itself specifies, so filtering patterns filter your data. These don't change your data, they just filter your data. And one of the interesting patterns in the filtering pattern is the Bloom filters. And we will have a discussion on that later in the slides. Then we have the data organization patterns. These are patterns, okay, let me just explain this with a little bit of example. So, so the unstructured data you have out there, okay. Now, for example, the data you get out of Twitter. Now, if or for example, you have some data coming out of Twitter, and then you have some data which is coming out of an RDBMS. You want to join these two things together and put it in a hierarchical format so that the processing on these things become faster. So generally the very structure of the NoSQL databases. Okay, so for example, as DFS, you can go ahead and store structural data. In Database also you can do that. So, for example, you started with maybe 2 or 3 RDBMS tables, and you wanted to keep all this data together. So you move from a very structured data into a hierarchical sort of a data. These things are useful down the line for further processing. So, so the thing is, your these design patterns don't exist in isolation. Okay, so you do certain things using these design patterns, and down the line you do certain further things on outputs from these design patterns. Okay, so data organization pattern is one of the patterns which sort of changes the organization of the data in such a way that it's going to be useful for the pipeline of processes which come later down in the order. Okay, then we have the join patterns. Again, join patterns is about you have multiple sources of data. You want to extract more value out of this, so you join these and do queries on it. So join patterns are useful for that purpose. Meta patterns, they're not exactly patterns in the real sense of the word, but they're very useful because what you have in these patterns is more about doing chaining of the jobs. Okay, so I was talking about so in any complex system that you build, your one iteration which comes out of your MapReduce job probably is not going to be enough for designing the whole system. Okay, so you will have to have a complex reorganization and combining of the iterations which are produced by each of these. So meta patterns come in use over there. Then we have the input and output patterns. These are things which help help with some of the tasks that you do with MapReduce. Graph patterns, interesting, and also interesting from the point of view of the fact that the graph algorithms are not very correctly suited for implementing on MapReduce. But then these patterns will help you resolve some of those problems. And actually, as part of this course, you will do an implementation of, I think I just told you this, so implementation of the PageRank algorithm. And that will be MapReduce, as the graph algorithms and MapReduce. There are a few more. We can talk about these things when we get to the course. So the course project. Okay, so as we have seen, so all these patterns are cogs in the wheel of a larger system. If you understand the components of these, chances are you'll have your way easier developing a complex system. Otherwise, you fend with your own ideas, and the good thing about these patterns is they have been perfected over the years. So different people have, in their own minds, tried to solve the same problem in different ways, and it turns out that there are certain best ways of solving certain problems. Okay, and then that's why it's good to know these patterns. But again, these are just cogs in wheel of a larger system, and will help you implement things from a very simple application to very complex applications. So as part of the project, we'll see, we'll implement a scalable inverted index. We'll see an example use case of an inverted index in the slides later on. But as part of the project, you will do something which is more scalable than the algorithm that we'll see here. Then you will implement two parts of the PageRank algorithm using MapReduce. You will use Bloom filters. You will do partitioning and sorting as part of building a search engine on the Stack Overflow data. And of course, joining. And a few more smaller patterns that you'll learn along the way. You will be using them. So now we come to the first use case here. We have seen why we need the patterns, what the patterns are. Now let's see how of these patterns. So let's talk about the first use case, and this is Stack Overflow inverted index. So in general, inverted indexes, again, it's a data structure. Okay, so it's a data structure like a map. From terms to a list of identifiers where those terms are actually present. That's a simple definition of this. And these are really useful when you have a huge data set and you want to do retrieval out of such data sets, then inverted index is just a necessity. You cannot do without that. But the good thing is inverted index is a very straightforward application of the MapReduce framework. And this derives from the fact that what you're basically trying to do in inverted index is you are trying to group things based on certain keys. And this grouping function is something which is very central to the MapReduce framework. So the examples where inverted indexes are used, of course, the search engine, which everybody knows about. And there the inverted index help in quicker retrieval of whatever search terms you have searched on. And then this is the other one is applications where you want terms to be annotated with further information. Now this is I'm not sure how many of you guys are familiar with text analytics. And in text analytics we do a lot of annotations. So there's a lot of algorithms where we try to figure out what this piece of data actually means. So we figure out entities in the text. It could be a person name, places, organization, and then even things more than that. Okay, so you could build an inverted index on the sentences being your map key, and the annotated terms on that sentence going as the value. This will help in your again the download processing of analytics on those initial text processing which is done here. Okay, so this slide is a schematic representation of the inverted index. So you have document 1, document 2, document 3. Of course, so we remove the stop word list from that, and then on the right hand side you can see the data structure which is built. So best is present in 2 different documents, blue in 1 and 3. Sorry, the best was present in the second document, and blue in first and third document, and so on and so forth. Here is the structure. Actually, the structure which I'm talking about, this is how I will be talking about the patterns when I talk about in the class. So we'll start with the description, then we'll look at the structure of those patterns with a diagram, and then we'll move at looking at the applicability of such things, then use cases of such things, and then examples based on that. Okay, so this is what explains your inverted index. So the mapper is taking in the documents, you have the keywords, unique IDs, going to the partitioner, and then the reducer combining those things down. So very simple, and just don't forget what is being done here is a pretty complex algorithm of creating inverted index on a huge set of data, and this small set of diagrams can explain everything here. Okay, so you understand the mapper part of this, so you understand. So combiners in this is not really useful because here most of the data that you have on the mapper side is actually going to be transferred in mostly verbatim form to the reducer side. So even if you try to combine something on the combiner side, it doesn't really give you too much involved, though in some cases where the output from your reducer is going to be concatenated together, then probably in those cases it makes sense to do the combiner. But again, that doesn't provide any benefit in terms of the bytes of the data which will be transferred across the network. Of course, partitioner is important here because there could be skew in the data. There are certain terms which will happen many more number of times than other terms which are very infrequent in the document. And now if you end up with skew in the data with a hash partitioner, the default partitioner, then you might be in trouble. So in cases where you have an idea as to there is definitely a skew in the data, or you have done some statistical analysis on this data before giving it to the inverted index, then it makes sense to write your own partitioner. The performance, we just, so if you look at the performance, there's nothing very complex being done. It's whatever time a MapReduce framework will take on your data in transferring from the map side to the reduce side. Apart from that, there's nothing involved. But the cost of the computation actually goes in the parsing of the content in the mappers. So, for example, if you are just building an inverted index on the words, then that's probably an easier job. But if you're doing an inverted index, for example, on, yeah, the sentence stuff I just talked about, right? Text analytics on sentences. So there's a significant amount of processing involved because you do tokenization, you figure out sentences in that document, then you go ahead and do parts of speech tagging over there, and then another set of entity recognitions on top of that. So that could be time consuming. But again, that's part of the computation cost of your job itself. There could be hotspots in the keys. We talked about that. Let's move forward. Okay, use custom partitioners in the case of skews in the index keys. And yeah, do remove your stop words and common words because you don't want to end up with a million document entries in your inverted index data structure. The use cases, we talked about these, the Google search engine. Then Wikipedia reference inverted index. Now this is one of the applications which is done on the Stack Flow data itself. So what it does is, so the references you find to Wikipedia inside of the posts and the comments in Stack Overflow data. Those things are actually can be added on a Wikipedia page, which actually reference back into the posts or the comments where those references happen. So that's about actually building an inverted index. Maintaining additional annotated terms, information on terms. So this I just talked about in the previous slide. That's the text analytics. And creating index on Overflow, Stack Overflow data. This is something which we'll do as part of the project. Okay, so let's see. So we'll do a short demo of the Stack Overflow indexer example. Here we are actually looking at the data which is available in the posts.xml and the comments.xml. Actually, these are very, very huge files. So the data which I'll use is going to be a subset of these. And our job here is to create an inverted index from terms to post ID or comment ID they refer to. Take care of removing stop words. So before we do this, let's look at the code for this. Okay, let's just a quick walkthrough of the code for this part. Can you see the code? Okay. So let's first have a look at the index, inverted index Stack Overflow. The main program is pretty simple. We have the mapper here, we have the combiner, we have the reducer. I've used a combiner here because I'm concatenating information from different records. I have a list of stop words which I add as a cache file here, and then I use this in the distributed cache in the mappers. Let's see the mapper here. Okay, so before the map is run, there is this setup method in which this stopword file is read from the distributed cache, and then the stuff is put in a list of string stopwords. Again, one thing you should keep in mind is using these kind of data structures, and probably in this case over here, the size is not going to inflate too much. But these can be scalability concerns if you are, if the context of your program is going to blow up this data structure, because you could easily get a out of memory error here. Okay, so in the mapper, it's a very simple thing which I'm doing. So the files I'm reading in these mappers are actually both the comments file and the posts file, and I distinguish these with using these two distinct fields which appear in those two files. So body and the text. So body appears in the posts and text is in the comments. Actually, set the keywords here and the value ID type. And then these keyword, the keyword is actually the word on which you are creating the map on, and the value IDs are the ones which you have. Only one document in which you have find this value ID. The reducer is also fairly simple. So I start doing a string builder in which I do append of all the values which are there for this term, which the reducer is processing, and then I write it out. Okay. Now I talked about a scalability concern here. The scalability issue actually comes here. One thing which I haven't done in the reducer here is most of the reducers, if you're doing a inverted index, they will go ahead and do an ordering on the values as well. So the MapReduce framework on itself doesn't do an ordering on the value, but here in the reducer, it's good to do an ordering on the value, because when you're doing searches, it's good to have the documents in which the term is happening, those documents sorted by their IDs. Now, doing that sorting will impose a lot of strain in terms of the memory on your reducer, and you could end up getting out of memory errors here. So we'll have a look at the scalable inverted index, and that's a part of your project that you will do in the course. Okay, so I think as far as looking at this code is concerned, it's fine. Now let's have a look at this. Just run this example. So the input here is containing close to, maybe the number of records are not many in here because we don't have much time in terms of running those. So 1,000, I think picked up 1,000 records from the posts and 1,000 from the comments, and then ultimately in the end you will see that an inverted index is built around the terms which appear in these two documents, and they will map from the terms to the IDs for these posts and the comments. And of course, the stop words have been used through the distributed cache. Okay, so I guess it's run. Let's have a look at the results. The result itself would not be very clean, because for getting a clean output you will have to do a lot of processing of the data. But still will give you an idea as to how this works. Just running. And there you have. Okay, I'll show you. So this is some of the data, and because we hadn't cleaned on the terms, so you see junk over there, but still junk doesn't mean that the execution was wrong. Things are fine because, for example, if you look at week, that seem to appear in these places. So in answers, in questions, and these are the IDs, and then you have the IDs. Okay. So keeping a watch on the time. Let's. So this is about the invalid index. Let's move on to the next one now, which is the Bloom filter. So we'll spend another 20 minutes or so on that. Okay, so Bloom filter, use case number 2. So what's special about the Bloom filter? So filtering, as you understand, right? So there is a set of data on one side, then you have a filtering test, and then if your data pass the test, you filter those things in, and rest of the things are discarded. Okay, so that's a very simple definition of filter. So what's so interesting about Bloom filters? So Bloom filters are interesting because of the fact that they consume much lesser data to store a filtering set. Okay, so let me give you an example here. For example, think about 1 million records on one side, and then you have a filter, and in that filter you say that I have got these 50,000 keys for the records, and I only want these 50,000 records, and then down the line I want to use these keys and go ahead and search for more information probably in an H-based database. Okay. So the problem here is, if you start comparing, if you take this whole data and start searching directly in HBase, you will end up have a lot of blocks of data which are being read into the memory, and because there's a MySQL set which you are going to use, and so the comparison that you will do on that data, most of the data which has been read into the memory blocks is going to be discarded. So we want to use a filtering option before we take things to a more expensive option that's actually reading from a database. Okay, so that's a more expensive option, and you want to minimize your bad data going to such a resource. Okay, so Bloom filter actually helps there. So Bloom filter helps by maintaining a set membership. Okay, so the records which have to be filtered in, they're actually part of a set, and anything which is part of this set is actually called hot values. Okay, now you might say, why is Bloom filter required for that purpose? Because you could use anything for that, right? You could use the set, 50,000 records goes into that set, and you just go ahead and compare in that set. Why Bloom filter? The good thing about Bloom filter is it takes much lesser space than a normal set of records that you will keep in a set will actually cost you. Okay, and this is this comes with a little bit of a cost, because you are doing good on as far as the space, memory space is concerned, but it comes with a little bit of a cost, and that cost is around some false positives going to the other side. So things which you know that these are actually not set members, but else they actually could get filtered in. But one thing which is made sure by Bloom filter is nothing which should not. So there's no false negative going to the other side. which is a good thing. False positives are fine, so you should not miss. So if you have false negatives being given out by Bloom filter, you will actually be missing records which should have been filtered in. But if you have false positives, that problem is not there, because what has happened is you wanted to have filtered maybe 50,000 records, and then you end up with maybe 50,500 records, which is fine, because ultimately you are going to test that stuff again down the line in the pipeline with a much costlier resource. Now that costlier resource you have avoided being wasted for things which should not have been proceeded to that stage. Okay. There are different ways of looking at Bloom filter. They can be seen as a join operation without caring for data values on the right. In some ways it is join operation because you have selected a certain set of records which you want to merge with things which are on the other side, on your right hand side of the filter. But this is without the records actually being joined from the databases. But you have actually picked up the right set of records. So if you do a join, you don't have to do the join on the whole thing. It can also be compared with a replicated join, where instead of replicating hot list everywhere, so hot list, for example, in our code, we are distributing the stop words list, right? That list was not too big, so I just spread that out everywhere using distributed cache. But Bloom filters could help in such cases because the size of the Bloom filter would be much lesser than that file that you're distributing. So as far as applicability is concerned, this is pretty simple because data has to be separated into records. Only then you can apply the filter, and then there has to be certain fields on which you can distinguish among these records. A predetermined set of items for the hot values. So these are the hot values on which you will train your Bloom filter. So I think I missed talking about this. Maybe I'll talk about in slides soon coming. Oh yes, this is here. So as you can see, the structure of the Bloom filter pattern. You have a training part in Bloom filter, and then the second part is actually searching part. Okay. So in this lecture, we're going to have a look at the Bloom filter training part, and then as part of the course, we'll have a look at the Bloom filter searching part. Okay. So training is quite important. So in this diagram, what I have shown is only one mapper. There's input split and one mapper. But actually, you can. So this would be fine in cases where you have the data that you're training on is not very high. But if you want to train on huge sets of data, it just makes sense to have multiple mappers. And then, the way you will design your algorithms again changes a little bit. In the Bloom filter mapper, we'll use a class which is provided by Hadoop. So that is called, that's known by the Bloom filter itself. Okay, I think it's talked about this. First, the filter is trained over the set of hot values. Trained Bloom filter object is stored in HDFS to be used during filtering. Filter needs retraining when hot list changes. Yeah, let me just explain this once more. So as I said, you need to train your filters, and they will be trained on the hot values. That's the set membership. The thing is, over time, these values can change, and whenever those values change, you will have to retrain your Bloom filter. Otherwise, the filtering operation won't be right. So this is stored as an object in HDFS, and then the next stage, which is searching in the filter, uses this object as the filter. Then on the bloom filtering part itself, you initially will load it from the distributed cache. The size of bloom filter is much more lesser. Each in the map function, this is actually only a map job. There's no reduce phase as far as the testing part is concerned. In training, you require a reduce phase. In map function, each record is set membership tested with bloom filter object. Output will be records that pass the membership test, and some false positive, as I said, are expected. Resemblances. So bloom filters are fairly recent as far as data analytics is concerned, but these filters have existed for quite some time, but might not have been useful when the world was not dealing with big data, because the very purpose of bloom filters is that you reduce the size of your data, the space that it actually consumes. So in such cases, definitely beneficial. So with the advent of big data analytics, bloom filters are being seen as being quite advantageous. Currently, I'm not sure as far as the PIG is concerned, there's a native implementation of bloom filters in PIG at the moment, but it can be implemented in PIG via the user-defined functions. As far as performance of bloom filters is concerned, it's very similar to basic filtering operation. Training the filter, of course, can take some time, but that's relatively infrequent. Oh yeah, that's some of the things we just talked about. Use cases, removing most of the unwanted values. So the example which I gave earlier had to deal with removing the unwanted values. Pre-filtering a data set for an expensive set membership check. Now if you want to do further analysis down the line, for example, checking things in HBase, then again, bloom filter helps. Reduce side join with bloom filtering. That's also a good use case. Okay, so now we will see an example of the bloom filter, and this is the training part. I'm not going to go into the testing part in this lecture. So the problem which we'll solve here is a hot list example. Okay, so in the stock overflow data, there are posts and the tags file, and tags.xml has a field called tag name. Train a bloom filter on 100 distinct values from the tag name field. Okay, so if I can paraphrase this question, there is we actually want to go ahead and search in posts.xml for tags which are present in which are these 100 distinct values, and we want to use a bloom filter for that purpose. Okay, so from the tags.xml file, there are multiple records in there, and each of these have a tag name. We have a file here which I distribute in the distributed cache, and from that we pick up 100 distinct values are picked up, and then only the records with those 100 distinct values actually trained on the bloom filter. Okay, and then at a later stage, these things will be combined with posts.xml.